Okay, hello everyone. Today we will be presenting Video-LLaVA, Learning United Visual Representation by Alignment Before Projection. This paper is by Lin et al. It's an archive preprint, and as of today, it has 12 citations. We are Group 1, David Chatwell Pitaluga, Anthony Bilek, Kevin Shai, myself, Zain Farhat, and Kunyangli. So I will first start by outlining our presentation. I will start by a motivation and with some background. Then we will go over the method. After that, we will go over our results, some ablations, summarize with a conclusion, some limitations, and future considerations. So for our motivation, we must first consider the various large vision language training paradigms. So the simplest one to think of is just the image-only training paradigm. These are for models like LLaVA, Instruct-Blip, Mini-GPT-4, where you have an image, you have corresponding text, you pass the image through an encoder, you project it so it could be represented for the sequence input for an LLM, and you pass it alongside with the text into an LLM. Now we can expand this to work not only for images, but for videos as well, such as Video ChatGPT, which is a video-only vision language model. So we have a video, we have corresponding text, you encode the video with a video encoder, you project it, and you pass it alongside with encoded text into an LLM. Now, another training paradigm is incorporating images and videos. So not only being limited to videos or images, but combining them. And the first paradigm we will go over is for one like video chat and Video-LLaVA, which uses a shared visual encoder. So you have an image, you have a video, and you have text. And the image and video are encoded in a shared visual encoder. Then they are projected also in a shared projection layer, and they are passed alongside with the text into an LLM. Another training paradigm similar to it is also images and video, but this time separate. This is for models, VLMs like Macau LLM and XLLM. So you have an image, you have video, you have text. The image is encoded in an image encoder. The video is encoded in a video encoder. They are projected separately, and they are passed along to that into an LLM, alongside the text into an LLM. Okay, now the two previous paradigms that we went for the images and the videos, they still fall inferior to a video expert model like Video ChatGPT. And this is attributed to the lack of alignment before projection. So the video and the images, when encoded, they lack a cohesive bind when passed into an LLM, which is why they fall short. And for this, there's the training paradigm called alignment before projection, sort of the one used by ImageBind LLM and Llama adapter, where you have an image, you have a video, and you have text. The image and video, let's say for ImageBind, are encoded with an ImageBind encoder, and we have this cache database, which just means that during training we will save the visual features of an image through a key value dictionary, such that when we perform inference, because for ImageBind you have multiple modalities, you don't want to use an encoder for each modality. So you just go to the cache database, you fetch your top K most similar visual features, you aggregate them, and you pass them alongside with your original output through a projection, and alongside with the text, these get passed into an LLM. So with that being said, let's go over our model architecture. And for us, we will first start with an image. In this case, it's the image for Statue of Liberty, and a corresponding video also of the Statue of Liberty, a text query. We will pass through an encoder, but for this we will use a language bind encoder and not an image bind encoder. And so just a recap on the language bind encoder. So you have different modalities: image, video, audio, and what you do is you encode them in the language in the textual feature space. So you want to pass all these into a dense feature space representation, and you want it to be in the textual feature space representation because the final input is to an LLM, which is powered by text. And then you have a shared projection layer, a word embedding layer for the text input. From this here, we get our visual tokens, and then we get our textual tokens. These are both passed into an LLM. In our case, it's a Vicuna v1.5. And our original input text query is, are the image and video depicting the same place? We get an output, yes, the video shows the Statue of Liberty from different angles, while the image shows a close-up of the statue. And now I will pass it on to David.
Okay, thank you, Shane. So now I'm going to talk about the training pipeline. And just as a quick overview, the pipeline consists of two stages. So the first stage is about image and video understanding. And here the objective is to align the visual representations to the input to the LLM. And for this, they basically fine-tune just the projection layer using image and video captions. And then the second stage is about instruction tuning. And here they fine-tune both the shared projection layer as well as the LLM using basically questions and answer pairs. So let's start with stage one. Here the image dataset consists of CC 595K, which was proposed by the authors of LLaVA. And this basically is a subset of CC 3 million, which goes through a concept balancing filter stage. And then they use a Blips cap fill to improve the captions, which results in 595,000 image text pairs. And then for the video dataset, they use Valley 702K, which comes from the authors of the Valley paper. And this is just a set of 702,000 video text pairs taken from the website Wikimedia. So during training in the first stage, the authors mentioned that they have a batch of both images and videos. And as Shane mentioned, they use the language bind image encoder and video encoder to encode the image and video respectively. And then they pass the resulting features into a shared projection layer, which the output is a set of between 1 and 8 visual representations, depending on the number of frames in the input. And these visual representations are also concatenated with a special image tokens to signal the LLM that these are indeed visual features and not text features. Then in the first stage, the text are just captions, like this, for example. This guy did an amazing martial arts stunt. He jumped on the mat and did a backflip and so on, which has a rich description of either the image or the video. And the text goes through a text embedding layer, which results in a set of text embeddings. And then all of these embeddings are passed to an LLM with frozen weights, which basically predicts the next word in the input text using causal mask. And the model is trained using a language model autoregressive loss. Then on the next stage, the image data set comes from LLaVA Mixed, which was proposed in LLaVA 1.5. And this dataset is basically a combination of 10 different datasets, some of which we have already seen in the past, such as VQA v2, RepCoco, OK VQA, and so on. So yeah, they combine all these datasets into a single one with 665,000 image text pairs. And then for video, they use the dataset from Video-ChatGPT, which, just as a quick reminder, the authors of Video-ChatGPT use videos from ActivityNet 200. And then they use these three models, Blip2, Grid, and Tag-to-Text, to generate frame-level captions. Then they check the consistency of the three captions for each frame. And finally, they use GPT 3.5 to aggregate the frame-level captions into a single video-level caption. And this results in 100,000 video text pairs. So during training, in the second stage, the visual branch is exactly the same as in stage one. So for each image or video, they generate a set of visual representations. However, in text now they don't have just captions, but they have a set of n question answers, a set of 10 questions and answers. For example, here the question 1 is what landmark is shown in the video, and the answer is the Statue of Liberty. And another question could be where is it located? The answer is in New York City. So this text is also goes through a text embedding layer, which generates a set of text representations. And then both the visual representations and text representations are also passed into the LLM, which now has unfrozen weights. So these weights are updated during training. And they also have an autoregressive language modeling objective. But this time, instead of predicting the whole text, they just focus on predicting the answers.
Okay, so this part we will talk about the performance of the Video-LLaVA, and first we will talk about. All right, thanks. Okay, first we will talk about the level-shot image question answering. And for this first part, we use 5 academic image question answering data sets for evaluation. And we can see through this table, compared with the SOTA model instructed billing 7 billing, Video-LLaVA still have the quite excellent performance across all these 5 data sets. And notably that even using the quite similar training data set for training, Video-LLaVA still had a quite good competitive performance across all the data sets evaluation. And on the whole, we can say that through these 5 data sets, Video-LLaVA has the best performance on the 4/5 data sets, and second on the data set with width. Which demonstrates strong understanding ability in natural video environments. And second, we use the image benchmark toolkits for border evaluation. So before delving into these tables details, we will first introduce these 4 metrics that pose. All right. MM bench, LLaVA bench in the wild, and MML wet. So for the poll, it's a polling-based method, which is used for better evaluation for the hallucination detection problem. For the poll, it first extracts the ground truth objects in the image, and then conducting the negative sampling using the 3 strategies. So the process is just like this. And for these strategies, it's separately the random selection. We just choose the non-existing objectives randomly in these things. And for the popular strategies, we just choose the non-existent objects most frequently appears in the same thing. And for the adversary strategies, we choose the non-existent objects quite similar to the existing objects in these things. So based on these settings, we will ask the models, is there the non-existent object in the image? If the models answers yes, polling will be added. So through these methods, we will evaluate the hallucination detection abilities for the models. And let me see. The smaller the value and the better the performance of the method. And second is about the MM bench. It develops a comprehensive pipeline that comprises of 2 elements. One is a data set, which surpasses similar existing benchmarks in terms of the number and variety of evaluation questions and ability. Second is a novel strategy named circular evaluation that is designed to convert freeform prediction into predefined choices. Just like this example in the feature, we can say for the problem, how many apples are there in the image? The matrix will ask the model many times with the circular shifted choice, and the model needs to succeed in all of the testings. But in this example, we can say that the model fails the pass rate, so it will be evaluated as fails a problem. And through this method, we can evaluate the model's performance, and the bigger the value and the better the performance of the model. So third is about the lava bench in the wild. So for evaluate the models in more challengeable task and generate the ability to novel domains. These benchmarks collect a diverse set of 24 images with 60 questions in total, including like indoors, outdoors, paintings, and so on. And it also provides an extremely detailed notation for each image and a prompt selection of questions. So take example for this image about the freezer. It will ask that what's the brand of the blueberry flavored yogurt. So obviously, it requires the model to extract details from high-resolution image and to have a broad knowledge coverage to answer this question correctly. Also, the bigger the value, the better the performance of the model. So last is the MMOAT. Different from the conventional benchmarks, which where they only focused on one or two capability, like the Wiki-V2 dataset, they only focused on the recognition capability of the model. The MMOAT focused on the various capabilities. They try to integrate the vision model capabilities together to have an evaluation like the recognition, spatial awareness, OCR, math, and so on. So based on the also the for this evaluation, the bigger the value, the better the performance of the model. And based on these four metrics, we can say from this table, Video-LLaVA still have the best performance across these last three metrics compared with the model shown on this table, which demonstrates a strong understanding of thematic aspects of things of the Video-LLaVA. Also, it can show that it can answer open-ended and free-form natural language questions about images. And also for the hallucination evaluation that we mentioned, whole evaluation setting, Video-LLaVA also had the best performance in all these three settings that was very popular random. So it can validate the consistency between unified visual representations and the generation of textual description. And so about the image understanding task, we will take a simple example to show its performance. So for this image, based on the instruction, what happens when the glove drops? Video-LLaVA not only can answer the question what was going to happen, and also can recognize the glove was red and the ball was blue. Whereas the ChatGPT-4's answer was unknown. So it shows the Video-LLaVA's response is more comprehensive, intuitive, and logical. And above is about image understanding task. Next, we will talk about zero-shot video understanding task. We can see from this table that Video-LLaVA compared with the video ChatGPT, it had the best performance on all of these four data sets, and that can validate that it can comprehend videos and provide contextually appropriate responses based on instructions. And this is a random video we select. And when we input the instruction, why is the video funny? We can say that Video-LLaVA will say, will extract the key information according to instruction and explain why it's funny. Because a baby reading a book while wearing glasses, which is the humorous side. But compared with this, video ChatGPT's answer is much weaker. It can just say that maybe he's learning to read. Also, for the image video joint understanding task, we can say from this example, both on giving image and its related video, and input instruction are the instruments in the picture used in the video. The Video-LLaVA can answer correctly, yes, the instruments in the images are used in the video. So through these examples can demonstrate the ability of the Video-LLaVA to understand inputs composed of both images and videos simultaneously. Yeah. Next is about the ablation.
Okay, thank you. So let's go over the ablations. So first we look at the effect that joint image video alignment has. We see that it is much more effective than doing them separately by this graph here across all these data sets. We continue to look at that, and we look at some VQA. We see overall it still performs much better when we unite the alignment, the encodings. And then when we look at videos instead of images, we see that there's improvement as well, especially for objects that are not inside the videos. We see that this alignment is more effective. And this chart also further exaggerates that point. Overall, across many data sets, this alignment is very effective. And those are the end of the ablations. They were very quick. And this is the end of the presentation, but let's go over it. So there's the Video-LLaVA is essentially an extension of LLaVA, but with videos. What it primarily does is it aligns before projections with language bind. We do training with images and videos as opposed to separately. And some limitations for Video-LLaVA are that it struggles with spatial temporal localization, which extends to struggling with long-range video understanding. And so the authors propose that we can improve this by maybe embedding timestamps into the training. And finally, we could extend the approach with adding more modalities. Okay, thank you.